Okay, let's unpack this. We spend so much time obsessing over the output of AI these days. The essays, the code, the weirdly accurate poetry.
Right.
But we rarely talk about the input. When you type a sentence into a computer, before it can do any thinking, before it can be smart, it has to figure out what on earth you just
It
said.
has to, yeah.
It has to turn that chaotic string of characters into actual structure.
It's the invisible step. We call it parsing. And you're right, it feels trivial to us because, well, we do it unconsciously.
Yeah.
But for a machine, looking at a sentence is like looking at a Rorschach test. It's an absolute nightmare of ambiguity.
That is exactly what we are diving into today, parsing. And the source material we have is fascinating because it spans the whole history, from the old school grammar rules diagrammed on a blackboard to, the modern probabilistic models that power things like Siri or ChatGPT.
A huge leap.
Yeah, so the mission for this deep dive is to figure out how a machine moves from seeing a string of letters to understanding who did what to whom.
And to understand why that is so difficult, we have to start with the villain of the story, the thing that keeps computational linguists up at night.
And that is?
Ambiguity.
The source material opens with this perfect example. It's a sentence that looks completely innocent. If I said to you, they saw some change in the market, you know exactly what I mean.
Right, they saw some change in the market. If you're a human, especially one who reads the news, you know that they refers to people, maybe investors, and they noticed a shift in economic trends.
Simple. But the text breaks this down to the eyes of a parser, a computer program, trying to label every word without any real-world common sense. And it turns into a disaster.
It really does. Let's strip away your intuition. Look at the word saw.
Okay.
It's the past tense of to see, but the dictionary tells the computer it is also a noun, a cutting tool, a handsaw.
Okay, but they handsaw some change.
No, that doesn't make any sense.
So you can't verb a handsaw.
Well, actually, in English, you can verb almost anything. But even if saw is a noun, you could theoretically have a noun-noun compound, like they are a specific group called the they, and they have a saw. It's unlikely, but a parser has to keep that option open.
Wow. Okay, that's a stretch, but I'll give it to you. What about change?
Change? Is it a noun, like loose coins in your pocket? Or is it a verb, to transform?
And what about some? That seems straightforward. It's a determiner. Some amount.
Usually. But it can also be a pronoun referring to some people, or it can even be an adverb meaning somewhat.
So if I mix and match these, I could technically read the sentence as, they used a cutting tool on some loose coins.
Or they saw some people transforming, or they saw that the market was somewhat changed. The source notes that when you combine all these, you get a mess. And we haven't even touched the structure yet.
The famous PP attachment problem, which sounds like an email error, but I gather it's about prepositional phrases.
It is the classic headache. In the market. What is that phrase attached to? Does it modify change, meaning the change is physically located inside the market?
Like, I found some loose change in the market.
Exactly. Or does it modify saw, meaning the act of seeing happened while they were at the market?
Right. I saw him while I was in the market.
Precisely. And to a computer, both are equally valid grammatical trees. The source cites a study, Church and Patil, from 1982. They showed that as sentences get longer, these ambiguities don't just add up.
They multiply.
They multiply exponentially. A standard sentence in a newspaper can have hundreds, sometimes thousands of theoretically valid grammatical structure.
Thousands.
Thousands.
And the parser has to pick the one correct tree out of that entire forest, usually in a fraction of a second.
That is the challenge.
So how did they try to solve this historically? Because I assume the early computer scientists didn't just throw up their hands and give up. The source talks about the rule-based era.
This was the intuitive first step. If you want a computer to understand English, well, you write down the rules of English. We called these heuristics.
So you'd literally code things like, if the word the appears, the next word is likely a noun.
Exactly. Or for that preposition problem, maybe a rule like, always attach the preposition to the closest noun.
Which is called right association.
Right. So in saw the change in the market, you'd attach market to change simply because it's closer. And that works. Sometimes.
But sometimes isn't good enough for understanding language.
It was incredibly brittle. That's the word the text uses. The moment you run into an exception, and English is basic 3 languages in a trench coat, so it's full of exceptions, the system just breaks.
Right.
Plus, think about the labor. You need armies of linguists writing rules for every possible sentence structure. It just doesn't scale.
Which leads us to the big shift in the late 1980s. the tree bank revolution.
Mm.
This feels like the moment where we stopped trying to teach the computer the rules and started asking it to learn them.
That's a fair way to put it. Instead of coding the rules, researchers realized they needed data. They needed a tree bank.
It's a great name, by the way, a bank of trees.
It's literally that. A tree bank is a massive corpus of text where every single sentence has been manually parsed by humans. Linguists sat down, took a sentence, and drew the syntactic tree.
They labeled everything, the noun phrases, the verb phrases, subjects, objects.
All of it. They did the hard work so the computer wouldn't have to guess.
And the famous one mentioned in the text is the pen tree bank.
The gold standard, roughly 1 million words, mostly taken from the Wall Street Journal.
I want to pause on that because it is genuinely funny to me. For decades, our cutting-edge AI learned how to speak English by reading 1989 financial news.
It is a bit funny, but it was necessary. By feeding those million words into the machine, the computer could stop guessing based on rigid rules and start calculating probabilities.
So it could look at the data and say,
It could say, okay, in 90% of cases in this data set, saw is used as a verb, not a tool.
so it's playing the odds.
Exactly. This is the birth of probabilistic context-free grammars, or PCFGs. But knowing the probabilities is only half the battle. You still have to actually build the structure.
Right, you still have to process the string of words into a tree.
Mm-hmm.
And the source outlines two main ways to do this mechanically. The first one is shift-reduce parsing.
Think of shift-reduce as the fast and greedy approach.
Greedy.
In computer science, a greedy algorithm is one that makes the best choice right now without worrying about the future consequences. It uses two components, a buffer and the stack.
Okay, lay it out for me.
The buffer is just the queue of words waiting to be processed. The stack is your workbench. Imagine a literal stack of trays or plates.
Got it.
You take the first word from the buffer, say the, and you shift it onto the stack. Now, the is sitting on your workbench. Then you take the next word, mark it, and shift that too.
So now I have the and market on the stack.
Right. And the parser looks at those two items and checks its rules. It says, hey, the market looks like a noun phrase. So it reduces them. It combines them into a single block labeled NP.
It's like Tetris. Blocks fall in, and if they fit a pattern, they clear out and become a bigger block.
That's a perfect analogy. And just like Tetris, if you place a piece wrong early on, the whole game piles up and you lose.
So if the parser decides too early that saw is a noun and reduces it,
It might get to the end of the sentence and realize, wait, I have no verb left in the buffer.
but it can't go back.
Not in a simple shift-reduce system. It's a one-way street, that's why it's fast, but it can paint itself into a corner.
So it's speed over accuracy. What if we want accuracy? What if we want to consider every possibility?
Then you use tabular parsing, often using the CYK algorithm. This is the thorough approach. Instead of making one greedy choice, it considers every possible choice.
But you just said there could be thousands of possibilities. If it builds all of them, wouldn't the computer just explode?
Yeah.
Or at least run out of memory?
It would if it built them all as separate trees. But the CYK algorithm does something brilliant. It builds a parse forest.
I love that term. A parse forest.
It relies on two concepts, subtree sharing and local ambiguity packing.
Okay, those sound like moving jargon. Let's decode subtree sharing first.
Think about efficiency. Go back to our example, in the market.
Okay.
Whether change is a noun or a verb, the phrase in the market is always a prepositional phrase. Its internal structure never changes.
Right. In is the preposition. The market is the object.
Exactly. So the computer builds that branch of the tree once, just once. And then for all the hundreds of different full sentence interpretations, it just points to that one pre-built branch. It recycles the work.
So it's not building 1,000 separate trees. It's building one massive web that shares the common parts.
Correct. And local ambiguity packing is similar. If there are two ways to analyze a small chunk of text, maybe some change is a noun phrase in two different ways, but they both end up acting as a noun phrase.
You just pack them into one box.
We just pack them into one box. We say, here is a noun phrase node, and inside it are two options. We don't let that small ambiguity ripple out and double the work for the rest of the sentence.
So we have this forest of possibilities packed efficiently. How does the PCFG, the probabilistic grammar, help us pick the winner?
It assigns a score to every rule used in the tree. The probability of saw being a verb, the probability of a preposition attaching to a noun, and so on. It multiplies them all together. The tree with the highest total probability wins.
But the source points out a major flaw here, the context problem.
Yes, A basic PCFG is actually quite dumb about specific words. It cares about categories, noun, verb, adjective. It doesn't really care which noun or which verb.
The example given is comparing they saw some change in the market with they saw some change in the afternoon.
Structurally, those look identical to a basic parser. Noun, verb, noun, preposition, noun.
But you and I know that in the market tells us where the change is, and in the afternoon tells us when they saw it.
One attaches to the noun change, the other attaches to the verb saw. But because the PCFG just sees preposition followed by noun, it treats market and afternoon exactly the same.
And it gets one of them wrong.
It often gets one wrong because it lacks lexical sensitivity. It needs to know the words, not just the tags.
And the fix for this was what? Teaching the grammar about specific words.
Essentially, we call it lexicalization or parent annotation. You modify the grammar so it doesn't just say noun phrase. It says noun phrase headed by market or noun phrase headed by afternoon.
So the label itself carries the key word.
Yes. Once you do that, the statistics can effectively learn that afternoon is a time word and has a high probability of attaching to verbs, while market has a high probability of being a location.
That seems like it would make the grammar huge.
It explodes the size of the grammar. Instead of 50 rules, you might have 50,000, but it's necessary for accuracy.
So far, we've been visualizing trees, big blocks of noun phrases and verb phrases. But the source takes a turn and introduces a completely different way of seeing the world. Dependency parsing.
This is a shift from constituency, which is grouping words into boxes, to dependency, which is linking words with arrows.
So no more noun phrase boxes.
No. In dependency parsing, we just look at the words. We say there's a governor, the boss, and a dependent. In the phrase, the big dog, dog is the governor.
And big depends on dog.
Exactly. We draw an arrow from dog to big, and an arrow from dog to the.
Why change methods? Is this just a stylistic preference for linguists who like arrows better than boxes?
It's actually about the type of language you're dealing with. Phrase structure trees. The boxes work great for English because English has a very rigid word order.
Subject, verb, object.
Right. But try parsing a language like German or Czech.
Why? What do they do differently?
They have free word order. You can take the object of the sentence and throw it to the front for emphasis. You can put the subject at the end. The words can be scattered.
So if you try to draw a phrase structure box around the object, but the object is half at the beginning and half at the end.
The box would have to stretch across the whole sentence and it gets very messy. But a dependency arrow?
The dependency arrow doesn't care about position.
Exactly. It just links the verb to the object, no matter how far apart they are physically in the sentence. It's much more flexible.
The source mentions that we use data-driven approaches for this too. Graph-based parsing. That sounds similar to the parse forest we talked about.
It is similar in spirit. Imagine a web where every single word in the sentence is connected to every other word. The computer assigns a score to every possible link.
So dog embarked, get a high score.
Exactly. And the embarked get a low score, and then it just finds the maximum spanning tree. It's an optimization problem. What set of arrows connects all the words with the highest total score?
There's one concept here that I found really hard to visualize, but the source makes a big deal of it. Non-projective dependencies.
Yes. This is the geometry problem.
It sounds like a geometry problem.
Think of the words of a sentence written out in a line on a page. Now draw the dependency arrows as arcs above the words. In English, those arcs almost never cross each other.
Okay, so the rainbow arcs stay separate.
Usually. But in some cases, and in many other languages, they have to cross. The source gives the example. They saw some change yesterday in the market.
They saw some change yesterday in the market.
Think about the relationships. Yesterday is an adverb. It modifies the verb saw.
Right.
In the market modifies the noun change.
Okay.
But yesterday is sitting right in the middle. If you draw an arrow from change to market and an arrow from saw to yesterday, those two lines physically cross each other.
I see it. The saw arrow has to jump over the change arrow.
That is a non-projective dependency.
And I assume standard algorithms hate that.
Most basic algorithms assume lines never cross because it makes the math much simpler. Handling non-projective dependencies requires much more complex logic.
We've covered trees, we've covered dependency arrows, but there's one final layer in the source that seems to go deeper than just grammar. Feature structures.
Right, because sometimes getting the tree right isn't enough to get the meaning right. Trees are surface level. They show you the skeleton. Feature structures are like the organs in the DNA.
The example is, they expect to go.
They expect to go. Grammatically, they is the subject of expect. That's easy, but who is actually doing the going?
Well, they are.
We know that. But the tree doesn't explicitly draw a line between they and go. To go is just a clause hanging off the end. If you want a computer to answer the question, who went, a simple tree might not tell you.
So feature structures fill in that gap.
Yes, a feature structure is a detailed dossier attached to every word. It lists attributes: person, number, tense, gender.
So they has a tag that says number, plural, person, third.
Exactly. And the mechanism to check these is called unification. It's not just gluing words together, it's logical deduction.
How so?
Think of it like puzzle pieces with very specific shapes. If the subject has the feature number, plural, and the verb has the feature number, singular, unification tries to combine them and fails. The logic breaks.
It's like a consistency check.
It is. It ensures that the deep meaning is consistent. It's the most linguistically accurate method we have, but, and here's the recurring theme, it is expensive.
It's expensive computationally.
And manually, you can't easily learn these deep feature structures just by reading the Wall Street Journal. They usually require handcrafted grammars, so while they are powerful, they are harder to scale.
It seems like the whole history of parsing is a trade-off. We went from handwritten rules, which were precise but fragile, to massive statistical models, which are robust but can be dumb about context.
And now we're trying to add the precision back in with things like feature structures. It's a great summary. We moved from telling computers how to parse to giving them data so they could learn to parse. But the fundamental problem remains.
Human language is messy.
Exactly.
And that leads to a thought I had while reading the end of the source. We talked about the Wall Street Journal being the training ground, the Pentry Bank.
Yes, the foundation of modern parsing.
If our foundational understanding of English syntax for AI is built on 1980s financial news, are there practical limitations to that?
Absolutely. The source explicitly mentions a fascinating detail. The Wall Street Journal contains almost no questions.
Your questions. It's a newspaper. It reports facts. It says the stock dropped. It rarely asks, where's the CEO, or why did the bond market crash?
So a parser trained on that might be surprisingly bad at understanding a question.
Exactly. The grammatical structure of a question inverting the subject and verb is rare in the training data. So the machine might struggle with the one thing users do most.
Ask questions.
Ask questions.
That is wild to think about. We assume the AI knows English.
Yeah.
But maybe it just knows journalism.
It's a blind spot. And as we move into this era of large language models, we have to ask, what is the new Wall Street Journal? What functional limitations are hidden in the structures of the new data we are feeding it?
A fascinating thing to consider. Next time you ask your phone a question and it gives you a weird answer, it might be looking for a stock ticker.
It very well might be.
That's it for this deep dive into parsing. Thanks for listening.
Thank you.